There's this whole load of change basically happening in the Arctic, and I think the sea ice forecast can help plan and hopefully mitigate against some of those changes that we don't really know are going to happen.
The Arctic is a region on the front line of climate change and has seen substantial warming over the last 40 years. AI forecasting tools like IceNet have the potential to fill an urgent gap in bolstering sustainability efforts. In this episode, we'll explore what IceNet is and how it can be applied in the aid of prediction, conservation, and communities in the Arctic. Welcome to the Turing Podcast, where we explore how data science and AI are helping society navigate the biggest challenges of our time. I'm your host, Amelia Jabry, and with me today is our co-host and resident expert, Dr Sophie Arana. Hi.
Hi, good to be here.
Yeah, great to have you, Sophie. You said that you're a research application manager here at the Turing. What does that role entail?
Yeah, so the research application manager role is actually something that the Turing has pioneered. And it's essentially a research infrastructure role. So it means we work with research teams, and we're all about bringing AI innovation into application. So looking for where could AI pipelines being operationalized, and essentially thinking about how to have impact in the real world with the research.
Great. And what kind of projects have you been working on to bring them to the real world?
I work with Luisa van Zeeland's team here at the Turing. So they are trying to build a multimodal and flexible sea ice forecasting pipeline based on the existing IceNet pipeline, which I'm sure we're going to talk about more.
Yeah, so what is IceNet and how does it work?
So IceNet today is really, I'd say, an open source ecosystem for sea ice forecasting. So 4 years ago, IceNet was, I guess, a very specific AI model that predicted sea ice. And since then, it's kind of developed into a whole ecosystem with a lot of work across the British Antarctic Survey and the Turing Institute.
You mentioned it's an AI model. So how does that make that unique?
So the original IceNet, which was published in 2021, was a UNet architecture. So that's a convolutional neural network, which essentially reads in sea ice concentration data from satellites and atmospheric data, and then learns to forecast or predict what the sea ice concentration will be in the future at, 3, 6, 9 days, months ahead of time.
Right. And how do forecasting models like IceNet differ from traditional physics-based models?
Yeah, so the traditional physics-based models are a lot more complicated in a sense and slower to run. So they're essentially, you have models for each physical component. So you would have a model for how the ocean behaves, a model for how the ice behaves, a model for atmospheric conditions. And then you actually have to couple all of these.
Physics-based models currently are still being quite widely used, but they're now being used in conjunction and potentially being replaced by AI models due to you said that the kind of ease of use and potentially better predictive capabilities too.
I would say we aren't quite there yet. So operationally, it's very much mainly physics-based models. I think there are maybe 1 or 2 AI-based models that are being used, but the way sea ice information kind of gets to the end user currently is often through kind of vetted authorities, so ice centers, Met offices, and they actually still have a lot of human analysts that, look at satellite data, look maybe at a physics-based model, potentially maybe if they have access, look at an AI model, but then kind of take all that data in and turn it into actually what's called an ice chart, which is literally a map of the ice, a very complicated map that people kind of need to learn how to read because it has specific codes. But those maps are essentially like vetted outputs that people on the ground navigating ships or making taking important decisions around conservation management would rely on those approved maps of sea ice.
So at least for the present, human expertise in reading satellite data, understanding the models and creating vetted outputs are still vital. However, AI models like IceNet help speed up and streamline the processes that are being shown to have better predictive capabilities over different timescales to physics-based models. And Ellie, I see you nodding along and ready to jump in. I would like to introduce our guest for this episode, Dr. Ellie Bowler, a machine learning researcher based in the Artificial Intelligence Lab at the British Antarctic Survey, who uses IceNet for her own, very cool, research.
Yeah, thank you. Nice to be here.
Nice to have you on the show. So Sophie and I were just chatting about the history of IceNet and about AI forecasting. You are using this on the ground with your research, so I'd love if you could tell us a little bit more about that.
Yeah, sure. So I work in the AI lab at the British Antarctic Survey. I've been there for about 4 years now, and my background's in sort of maths and machine learning, but I particularly look at applications for wildlife monitoring and conservation. So I work a lot on sort of other detection problems, like detecting animals in drone and satellite imagery. But then more recently, I was involved in the IceNet work, seeing if those forecasts could help guide conservation and management decision-making for particularly Arctic species. And we had a case study looking at caribou specifically.
For the listeners who are maybe not aware, because I definitely wasn't at the beginning of this, what are caribou?
Oh, yeah. So caribou are, I guess, in Europe, we'd call them reindeer. The caribou we were looking at here in Canada. So it's kind of the same species, but different for reindeer.
Yeah. And my question to this is, why is sea ice hard to forecast?
I think it's, it has these quite complex interactions because it's influenced by the ocean. So like the temperature, the waves, but then also the atmosphere. So it sits at that kind of boundary between those two, which in themselves are quite hard to predict systems. And then I think the ice itself has a lot of quite unique characteristics. So it can be different thicknesses that will depend how it forms and how it melts. It can be different age. It can, there's all these different parameters of the ice itself. Obviously, there's increasing impacts of climate change. I think even without climate change, actually, sea ice naturally is very dynamic and quite unpredictable as a kind of system. So knowing when the ice is going to freeze over exactly at a really local scale, for example, might be challenging. But that challenge is becoming more exacerbated by climate change, that we're seeing crazy kind of sea ice conditions in the Arctic.
And especially at the marginal ice zone. So that transition between the open water and the coastline, there is a lot of the dynamics that Ellie just mentioned really come to play. Where kind of like there is a mixture of newly forming ice and ice flows, and there are waves interacting. And I think that's like a notoriously hard to predict region for AI models specifically.
Yeah, I think this is where AI techniques have sort of shown an ability to kind of extract and learn those really complex interactions in a way that perhaps the physics-based models maybe were capturing some of that, but there were elements that maybe we don't have incorporated.
Correct me if I'm wrong, Annie, but something I thought was really interesting was that in the original IceNet paper, I think the comparison against the leading dynamic model showed that IceNet performed best, I think, 2 to 6 month lead times. But you kind of validated IceNet again for that specific region where the caribou cross, so that the region that is relevant to the conservation. And for that region, the model actually outperformed at all lead times.
Yeah,
is that correct?
True. Yeah, that's right. And it's interesting because IceNet, and in the paper as well, it's a pan-Arctic model. So it is trained to optimize basically the prediction across the whole Arctic. And we had that analysis was kind of looking, well, in this very small region we're looking at, it may just be ignoring any kind of accuracy because it doesn't contribute a huge amount, I guess, to the loss in that case. It was really positive to see that the IceNet is able to outperform across all lead times.
I think it really shows how important that translational research element is. So even if you have validated a forecasting model globally or pan-Arctic for one hemisphere, it doesn't necessarily mean that it's going to perform worse or better for a specific region where the actual decision-making is taking place.
I think it's true because there's also different regions will have kind of different ice regimes, I think. So the one we looked at, it's seasonally frozen, and then in the summer it's always open water. It has, this sort of distinct transition, which is quite consistent.
Between frozen and open.
Whereas further north, it might be frozen most of the year, so it doesn't change as much.
You've talked about this freezing and melting cycle, which was the focus of a lot of your research. Can we dive deeper into that and the caribou that rely upon this cycle? What makes these particular caribou and their migration unique?
Yeah, so the case study that we did was looking at the dolphin and union caribou, which are a distinct population in Nunavut in the Canadian Arctic. And this was a project that we worked on in collaboration with the government of Nunavut. So some regional biologists there, Lisa Leclerc, Amelie Roberto Sharon. And they've, been studying the dolphin and union. So the thing that's quite unique about them is that the herd make this sort of big group migration across the ice in the Coronation Gulf. So they go to an island called Victoria Island, which is off the north coast of mainland Canada. And they travel north to Victoria Island in the spring before the ice melts. And that's where the females will have their calves and they sort of spend the summer and graze. And then in the autumn, they sort of congregate on the south coast and they wait really for the ice to reform before they can cross back to the mainland to overwinter. So
how long are these crossings in general?
So when the ice freezes over, they cross quite quickly. So the distance is not huge. It depends where, but it's anywhere between 25 kilometers to 75 kilometers, which is quite far for caribou.
Naturally, you can assume that things like climate change are affecting these crossings, potentially making them more variable, or maybe if the ice is not freezing up at all, that could be a real concern. The question is, so why are these migrations important? Like, why should we care if caribou can get to Victoria Island and back? Yeah,
so it's something where I guess there's an intrinsic importance in the herd, in the ecology of the region. They're endemic to that particular sort of area of Coquitlamont. But they also are very important for the lives and livelihoods of the indigenous communities in that area. So they form part of their subsistence hunting kind of culture and food security today. So they're incredibly important in the culture of the indigenous communities and cultural continuity going into the future. It's really important to put all the effort into conserving that herd. And then one thing that we looked at with this system was also the impact of ice-breaking vessels and increased shipping, which we're kind of seeing across the Arctic as well. So that can create added pressure on the herd, which is already facing these kind of combined threats from climate change, sea ice.
So are there actual tracks of the shipping stopping the ice freezing over as well?
Yeah, that's it. So they have in the Arctic ice-strengthened vessels. So they have a strengthened hull basically, and they can push through formed ice, which you need to navigate in some of these areas. And some of these vessels as well will be essential for say, like community resupply, delivering food and fuel and things like that.
Yeah, sounds like a very complex problem because you need one thing and it relies on another thing.
I guess we can also add that the caribou is just one example out of many ice-dependent species that are more and more kind of being disrupted by human activity in the polar region. So WWF has published a report on blue corridors where they mapped out whale migration patterns, and whales also, their migration patterns or their movement is highly dependent on the sea ice too. But there's also these bottlenecks across the Arctic where both whales and ships need to cross through like quite narrow channels, so they spatially overlap. And that creates a lot of conflict. So yeah, there's a lot of examples like this where animals are increasingly being disturbed essentially by humans. And it seems like our responsibility to try to minimize that as much as possible.
Yeah, also it's this human aspect that very much appeals to the anthropologist in me, as when I studied this in university, there's been a historic dependency of indigenous people following migratory routes for the hunting, for example, caribou and whales, as we mentioned, but also how this pattern of movement actually helps conserve and potentially alleviate stress from fragile Arctic land, although this is more historic as settlements are more permanent and no longer semi-nomadic. But keeping these migratory patterns does have a cultural as well as ecological significance.
Yes, exactly. And also maybe to bring it also again to conservation, I think you already mentioned that, we should care about wildlife in the polar regions because they're really important cultural and spiritual part of the local communities. They're also, part of their food system. But even for us who are maybe not hunting caribou or seals or whales, they also form, of course, a very important part of the entire carbon cycle. So, seals eat organic matter that drops to the ocean floor and is kind of stored away. So I think it makes sense to be concerned about these extreme changes because they will affect the entire ecosystem.
And from my side, I feel like that's a positive project to be involved with, because a lot of times you might be maybe monitoring change, or like the work I've done previously, it's a lot about monitoring wildlife and surveying wildlife. And yeah, sometimes the numbers go down, and that's, that's hard to feel like positive about. But I think if you can predict stuff into the future and get ahead of stuff and try and plan and obviously work with like the communities and build those kind of systems, it's like helps.
I love that point about the coexistence, because I totally agree. I think having the ability to predict on short timescales really is going to change how people and wildlife coexist together in the polar regions, right? Like a lot of current conservation is kind of very static. So you essentially, and a lot of policy involved, I think, where it can take years to establish a protected area, and then it has defined bounds, and maybe certain activities are not allowed in that bounds. Being able to kind of do that dynamically and react, I think, completely changes how conservation is going to work.
And do you know how this works alongside traditional conservation methods?
Yeah, so actually in the region, there's been a lot of focus on trying to manage risks to the crossing. And there's a group called the Victoria Island Waterway Safety Committee, and it's a big sort of combination of groups from the community and the national and regional governments. But they've sort of developed like a notice to mariners system, which is, it's actually, it's innovative in itself. It's not necessarily like a traditional conservation measure, but it's trying to get better communication basically between vessel operators and people in that region. Part of it was for human safety, because actually the ice-breaking vessels could pose a real risk to people as well. Mm-hmm. And there was a story of someone from Cambridge Bay that could have been cut off from the community because of an ice-breaking vessel. So that was like why it was probably raised as a real priority. But then as it's developed, there's interest in obviously putting in the Caribou migrations as well. So there is a notice to mariners system in place where the vessels are meant to give notice of when they're transiting through, so that the communities have early warning of that. And they in turn can communicate with vessels, and they're developing dashboards so they can see which vessels are transiting through.
So that's why prediction is so valuable in this aspect, because it's so complex. And so if you can conserve kind of the people's time and safety, as well as the caribou's ability to cross and the community's ability not to be cut up from itself, then the early prediction is incredibly vital. So this predictive modelling doesn't just have to be used to track caribou or whales, but it could be broadened out to other species too, right? I think I read in your paper that it could be useful for polar bears, for example, because they tend to venture towards communities when the ice melts, as there's less hunting opportunities out there. We
had a project, again, kind of just testing the forecasts with Amelia when she was doing a polar bear survey. So they did a big survey of the Fox Basin polar bear.
What's a polar bear survey?
So they try to get a handle on the number of polar bears, but it's a really big task because the populations of polar bears, actually, they cover huge areas and they need aircraft. This one was done by, so they have aircraft and a number of different stops. It kind of takes them 2 months to cover the whole region.
It's
a long time in the field. And so they were interested in having the forecast because it would help see if they were missing fragment areas of ice which might hold a lot of polar bears. That would skew their kind of estimates of the population abundance estimates if they missed them.
And just to jump in here, I had the pleasure to sitting in that feedback meeting with these researchers that ran the polar bear survey. And I think it was such a great example of how important that co-creation and that communication with end users is, because they were describing to us kind of all the decisions that they were taking as they planned the survey and executed the survey. And I think at some point we asked them about, was there anything that you saw from the plane that you didn't expect given our forecasts, right? And they were like, yes, actually, there was some parts where there was kind of broken up ice. And they explained to us how that has a huge impact on their survey because they have to fly a lot slower over broken up ice because it's very textured. So it's hard to see essentially if there is an iceberg or not, right? The contrast is like a bit harder to see. So they were like, it completely changes our flight duration and the whole planning. And I thought these little nuggets of information, you don't really have that insight into the operational side when you're kind of coding your model and doing that research. But being able to talk to them and ask, what does it actually look like when you're in the plane looking at the ice? That's really not sure. But I think they did say they were like literally counting based on what they saw.
Yeah. It just sounds like a very epic challenge to try and count polar bears from a plane over ice.
There was something that you said before that I just wanted to briefly emphasize because it's something I wanted to bring up anyway. So you said that the research software engineering that went into the actual delivery of the forecast. And I just want to emphasize that I think that's why it's so exciting to work with the IceNet team, because IceNet is no longer just, in quotation marks, just this one AI model, but a lot of kind of research, software engineering work has gone into building it up into a whole ecosystem. The digital innovation team at the British Antarctic Survey and also the software engineers at Turing, they have essentially, after the paper was published, have created APIs, turned the research code into a pip installable Python package, so something that other researchers and engineers can easily use again, run again, expand on, and so on.
Yeah.
And that type of groundwork is usually what's missing to take an AI innovation from academia into operations. There's essentially a lot of additional effort that goes into making it reproducible, making it accessible, and then being able to actually deliver it to an end user. So I just wanted to emphasize that.
Yeah,
that's a huge part.
It's a good point. It's not just the interface they've developed, it's all the back sort of behind the model, the data downloaders, because with the AI models, you are processing a lot of data. So I think when we have new researchers come on board and they want to develop a new model, it sort of takes away some of the effort, right, of recoding all of these data downloaders and stuff to process data. It's all there and it can be reused. So it's really neat what worth checking out.
And exactly. And it enables the type of work that you were doing, which is more translational. And then it also enables the work I'm hoping to do, which is to then drive building out the tooling such that an end user could actually, or not could actually use it. People can already actually use it, but do use it.
Yeah, it's really great to see how this development of this forecasting tool over time and how it's being built and improved and packaged with both researchers and end users in mind. So my question from this then is, where are we going? What is the big picture aspiration for something like IceNet?
The big picture, right? So I guess having that groundwork done now, I think there's a lot of opportunities, first of all, and I think, Ellie, you alluded to that in the beginning, to take new AI architectures, and there's so many kind of AI tricks that we have available that haven't been applied yet to that problem. So the CI's team is working on, and also the British Antarctic Survey is working on using diffusion models now.
And to jump in, could you clarify what a diffusion model is?
Yeah, I'll do my best. So the group at Turing I'm working with, so Maria Novitasari, is currently training diffusion models to reproduce and hopefully improve on IceNet's performance. So it's quite exciting. Essentially, a diffusion model is a different framework for learning that is coming from generative AI. So a diffusion models actually learn, rather than learning to predict a picture, they learn to predict the noise that you artificially infuse in the inputs. And by getting better and better at predicting that noise, they're then able to essentially remove the noise and reproduce very kind of high resolution, small scale features in an image. And yeah, I guess diffusion models have been really successful lately combined with language models and DALL-E and so on. This is where like our ability to reproduce very, very realistic pictures has come from.
Yeah.
And now it's being applied to these forecasting tasks.
So it's much better to forecast where the ice will be, and then therefore when you have peak ice, and so the Caribou can cross, if I understand correctly.
Yeah, that's it. In this project, we were interested in, it sort of emerged that these really high sea ice concentration values were important for getting an idea of when the Caribou would cross. So that was one of the main focuses of the paper, was seeing if we could link migration timing to sea ice concentration, and therefore use sea ice concentration as an indicator for the start of the migration.
And were you able to predict that?
Yeah, actually we found using the data that IceNet, the ICF data that IceNet was trained on, there's a strong relationship there. And that wasn't necessarily a surprise, because we knew from all the existing knowledge of the Caribou that they wait for the sea ice to form. But it was kind of reassuring that we could see that even in this quite coarse data product that we were using. And then we did see some promise even in this, first kind of development version of the daily model of IceNet, that it could get these kind of rough crossing times. So we sort of produced a few different outputs, like a map output and sort of time frames that the users could try and interpret. And so it sort of showed promise that if you can predict very high sea ice concentration values, then you could give it as an indicator for Caribou migration times.
So it looks like the future of IceNet is an ever-developing one, implementing these new AI architectures such as diffusion models, and therefore helping improve the model, its predictive capabilities, and in turn aiding conservation efforts and communities in the Arctic. That's all we have time for in this episode, so thank you to our co-host Sophie and our guest Ellie, who've expanded my understanding of sea ice and those who rely on it, and how AI models are bridging the gap of accurate prediction so the Caribou crossing to Victoria Island aren't faced with one.
Thanks for having us. It was fun.
Thank you.
If you enjoyed this episode and want to know more about IceNet or the Caribou project, or how the Turing and the British Antarctic Survey are helping tackle climate change, where can they find you?
All the IceNet code is actually open sourced. And so we also have a brand new website, so you can go onto icenet.ai, and there you find the GitHub pages linked and a lot of documentation and links to all the papers.
You can also like, share, and subscribe to the podcast. Sign up to the Turing mailing list to stay up to date on our missions. Head to turing.ac.uk to read about IceNet and our wider environmental work, or email us at podcast@turing.ac.uk. We'd love to hear from you.